Hello everyone! In this video, we're going to look at the difference between discrete variables and continuous variables and talk about why that matters in terms of our probability calculations. It is going to be really important in one specific situation to know whether we are dealing with a discrete variable or a continuous variable, as it will have a big impact on our eventual probability calculation. So first off, recapping what the difference between a discrete variable or a continuous variable is. When we are looking at discrete variables, they are variables that we are talking about counting things. So when we're counting, if I look at just numbers between 1 and 10, when I'm counting, I can only hit very specific values between 1 and 10. Again, those counting numbers, 1, 2, 3, 4, so on, all the way up to 10. There are only very specific, a limited amount of numbers that I have between those values. Whereas when I'm talking about a continuous variable, so a continuous variable is something that we would use for when we are measuring something. A continuous variable does not have that same limitation as a discrete variable. We don't only have a very limited set of numbers between two specific values. So again, if I look at between 1 and 10, well, if I'm talking about a continuous variable where I'm measuring, I don't jump from, say, from 1 to 2 to 3 to 4. I can measure more and more accurately with more and more decimal places. I don't go from 1 to 2. I may go from 1 to 1.1, or from 1 to 1.01. or 1.00000001. I am only limited by the number of decimal places that I want to measure accurately to. So, as we said, discrete variables can only take on a very limited specific amount of values between two set values, whereas a continuous variable can take on an infinite number of values between any two values. There is an infinite amount of possibilities between 1 and 10, or for that matter, between 1 and 2, or 2 and 3. Again, I am only limited by the amount of decimal places that I want to carry. So as we look at our impact on probability calculations, this is going to have a significant impact, as I said, in one specific calculation. So now let's continue on with the knowledge that discrete variables are very limited in the values that they can take on, whereas continuous variables are completely unlimited. They have an infinite number of possibilities between two values. So now taking that in speaking about it and how it relates to our probability talks, well, when we're looking at calculating a probability, what we're always going to be doing is, like I said, we're going to compare a sample value to a population value. Compare a value that we measured and see how that relates to what's going on in the entire population. Now, we learned way back at the very start of this course that there was something called sampling error. Now, what sampling error refers to is that as we take a sample, we are almost certainly not going to see the population value that we're supposed to see. We are not surprised when we take a sample and we don't get exactly what we're supposed to see. That is sampling error. If I say that the average age of people in Canada is 37, and then I go and I have 100 people in a room and I take the average age of the people in that room, there is almost certainly no way I'm going to get exactly 37 as my average age. That is sampling error. I don't get exactly what I'm supposed to see. But where the probability comes into play, we look at what is the population value that I'm supposed to be seeing and comparing that to a sample value that I'm actually seeing. Just because my sample value is lower, so I'm going to say lower because this sample value is on the low side of the distribution, where the population value is always in the middle. Just because the sample value is on the low side doesn't necessarily mean that anything is going wrong or there's anything that I don't expect to see. Sampling error tells me that that sample value is never going to be right in the middle. It's going to be hopefully somewhere in here, somewhere in the heart of that distribution, in the sort of part where we have the big hump, as opposed to in the tails. So when we have it close to the middle, when we have that sample value appear somewhat close to the middle, we have no indication that really anything's going on, and everything that we're seeing is really just a result of sampling error. When that sample value, however, is way out in the tail, we may have an indication that something is going wrong here. What we want to calculate in terms of probability is if our sample value is on the low side, what is the probability of getting a sample value equal to or less than what we just found? And when we get a sample value that's on the high side of the distribution, what we want to check is what is the probability that we get a sample value equal to or greater than what we just found. And then with that probability is going to allow us to make a decision. Is there something more than sampling error going on here or not? Is the fact that my sample value is not the same as the population value down to that concept of sampling error, or is there something that's indicating there's a problem with the sample that I've taken? So let's begin and look at what happens when we get a sample value on the low side first. So imagine I'm told that within some population, the value that I'm supposed to see is 15. Okay? Whatever that is. I'm supposed to observe a population value of 15. And then I go and I take a sample, and in that sample, I get a value of only 13. So now I have to go and calculate what is the probability of getting a sample less than or equal to 13. So there's two situations we might be in. We might be dealing with a normal distribution. And again, we had in a previous video, we talked about how we decide to which distribution we want to use. So if I go through that thought process and I end up deciding it's a normal distribution, the normal distribution relates to a continuous variable. Normal distributions are where we are measuring things. And as we've just seen, when we measure, we are only limited by the number of decimal places that I want to represent. There is an infinite amount of numbers between any two numbers. A binomial distribution relates to a discrete variable. A binomial distribution is where we're looking for success or failure. When I look at this item, does it exhibit the trait that I'm looking for or not? I can only have those set counting numbers. You cannot have an item that exhibits part of the trait. We don't count that. If it doesn't fully exhibit the trait, then it's a failure. If it fully exhibits that trait that we're looking for, then it's a success. So as we said, the normal distribution uses continuous variables. The binomial distribution uses discrete variables. So examining the normal distribution first, I'm supposed to see a population value of 15. I only see a value of 13, less than what I'm supposed to be seeing. So what I want to check is less than or equal to 13. Well, if we're using the normal distribution, then the function in Excel we would be using is norm.dist. And because I'm looking for more than one value, I'm looking for 13 and everything below 13, my final input into Excel will be 1. The only time I make this 0 is if I was looking for exactly 13 and nothing else. But here I want 13 and everything below. Well, when I put in 13 as my first input and 1 as my final input, this is exactly what I'm given in Excel. Excel gives me this value and every possible value lower than that. It is the same thing with the binomial distribution. So if I was supposed to observe a population value of 15 and I observe something less than that, 13, again, I want to check less than or equal to the 13 that I observed, knowing that I'm using binom.dist, and knowing that I'm not looking for just 13 and only 13, I want 13 and everything below, my final input would be 1. And once again, if I put my first entry as 13, again, that's exactly what it's going to give me. Having a first input of 13 and a final input of 1, what I will get out of binom.dist is exactly what I'm looking for, 13 and everything below. So when I'm talking about getting a sample on the lower side of the distribution, I see that within norm.dis and binom.dis, my inputs in certain aspects are very similar. I put the exact number of observations I noticed in my sample, 13. I put that I'm looking for not just 13, but everything less than that. Now, the middle two inputs are going to be totally different, but that first input and that fourth input are exactly the same. And I get exactly what I was looking for, 13 and everything below. Where the difference comes in the discrepancy between discrete and continuous variables comes to light is when we're dealing with a sample value on the high side. So imagine the same scenario where I'm supposed to observe a population value of 15. However, now I get a sample value on the high side. Anytime I have a sample value on the high side, what I need to calculate is the probability of greater than or equal to what I'm finding in my sample. So, for example, if I have a sample value of 17, I would need to calculate greater than or equal to 17. Well, we know that our distributions, norm.dis and binom.dis, don't work this way. They only work at looking for your value in below. If I want to look for my value in higher, I'm going to need to use my complement rule, 1 minus. Okay, so if I want, with the normal distribution, if I want to find exactly 17 and higher, because I'm looking for higher, I'm going to need to use 1 minus norm.dist. And again, I'm not only looking for 17, but I'm looking for 17 in every possible value higher than 17. So I want 1 as my final input, right? Only 0 if I wanted exactly 17 and nothing else. As soon as I say I want to be left with 17 and everything higher, that means what I need to get rid of is everything less than 17. I want 17 kept, and I want everything possibly higher than that. Well, with the normal distribution, when I'm talking about the fact that I have to get rid of everything below 17, the next value below 17 is not 16, it's not even 16.9 or 16.99. The next value below 17 is 16.999999999, and I can say those nines on and on forever. The difference between 17 and the next value lower, 16.999999999, is so infinitely tiny that we don't even take it into consideration. So when I talk about I want to get rid of everything below 17, I really just still include 17 here, even though the value in reality is 16.99999999999 on and on forever. There essentially is no difference between 17 and the next value possibly higher, the next value possibly lower. So anytime with the normal distribution, whether I'm talking about less than or equal to or greater than or equal to, I'm always going to enter the value that I found in my sample. However, here is the big difference. With the binomial distribution, that is not the same. In the binomial distribution, where I'm dealing with a discrete variable, those very specific counting numbers, if I want to find 17 and everything possibly higher, okay, so I was supposed to observe 15, that's my population value. In my sample, I observed 17. Well, because I want 17 and everything possibly higher than 17, again, I need to use 1 minus. My distribution function only works at a value and lower. Here, where I want to work a value and higher, I need to use the complement rule, use 1 minus. I'm not only looking for 17, I'm looking for 17 in every possible higher value. So again, my field 4 entry would be 1. But now when I talk about if I want 17 and everything higher than 17 kept, I want 17 and everything higher, meaning I have to get rid of everything less than 17. Well, the next number lower than 17 is now not 16.9999999 like it was with the normal distribution. The next value less than 17 is 16. I need to get rid of 16 and everything below 16 in order to be kept with 17 and everything higher. So here is the big difference and why it is important that we consider whether we're dealing with the normal distribution or the binomial distribution in the difference between the discrete and continuous variables that are contained within them. We notice that in all those situations, and remember, this is what we're going to be checking all the time going forward. What we want to do going forward is we will be given a population value that we're supposed to see. And then to that, we're going to compare a sample value, something that we measured. And I've got to decide, is this down to sampling error, or is there something more than sampling error going on? When we have, let me go back here for a second. When we have a sample value on the low side of the population value, we always want to check less than or equal to. When we have a sample value on the high side, we always want to check greater than or equal to. We saw that as we check less than or equal to, it didn't matter whether I was talking the normal or the binomial. I entered my sample value as my first entry, one as my last entry. They were both the same. Again, field 2 and field 3 will be different between the two. Where the big difference comes is once I start dealing with the binomial distribution when I'm dealing with greater than or equal to. The normal distribution, I still entered 17. I still entered the value that I saw. But the big difference, when I do 1 minus with the binomial distribution, if I want to be left with that sample value of 17 and everything higher, it means I need to get rid of 16 and everything below. There should be alarm bells going off in your head anytime you do 1 minus with the binomial distribution. Remember, there is something different with 1 minus with the binomial distribution that you don't see any other time. You don't see it when I'm doing less than or equal to with normal. When I'm doing less than or equal to with the binomial, I don't see it when I'm doing greater than or equal to the normal. But when I do 1 minus with the binom.dist, when I'm dealing with greater than or equal to with binom.dist, it is a very special situation where I need to make sure that my distribution starts one value less than what I observed in my sample, so that when I do the calculation, I am left with that sample value and everything above. Again, I hope this helps as we continue on with our probability calculations, as we move into our decision-making lessons and into our formalized hypothesis testing that we'll be dealing with in future units. This will come into play over and over and over. It is the most common mistake I see as we go forward in the course. Alarm bells. When you have 1 minus with the binomial distribution, something is different than in any other situation. Thank you. As always, please email me with any questions that you may have.